Welcome to the MSS Innovations Data Science Coordination Without Communication presentation. I'm Aaron Dant. I'm ASRC Federal's Chief Data Scientist and also the AI Technologist Fellow. I'm interested today in talking about our Coordination Without Communication technology. This is a technology we've developed in partnership with the Missile Defense Agency and work with the Navy. With multi-platform engagements where you have multiple weapon systems working together, the coordination required between them is very significant. If the comms environment becomes contested or the systems are unable to speak with each other, each weapons platform is left to identify its own target without being able to coordinate with the others. This can result in some targets being entirely ignored and others get engaged redundantly. This is not only wasteful, but it can lead to situations where in defensive fire, incoming threats are missed and end up hitting targets. We've developed a technique that allows predictive AI to generate a methodology for the weapon systems to know what the other platforms are doing in those scenarios. And we've demonstrated this technique for the Missile Defense Agency with 3 forward deployed AEGIS vessels in a hypothetical scenario defending against a raid of 9 intermediate range ballistic missiles attacking ground targets in Guam. In the demonstration we're going to show next, we'll have 3 different scenarios, one with full communication, one with a comms denied environment, and then another with our technology, coordination without communication, being employed. Coordination without communication uses artificial intelligence models to predict the behavior of other weapon systems to avoid redundant engagement. Many different companies focus on things like raid management and multi-platform engagements, where they essentially use a mathematical formula to identify the best possible shooter for a given situation. That all works fine until the comms are denied, and we're going to see what happens in those scenarios. With these short videos, first we're going to show a scenario 1, what we call commander coordinated. This is an example where we have a simulated commander, who we call Blue Force Commander, issuing orders to the 3 vessels to give them the best possible mathematically optimal solution for an incoming threat. In this scenario, you can see that there are 3 AEGIS platforms that are forward deployed around Guam in stochastic positions. These are obviously not real ships. You can see USS Aaron there. But in this case, we have a raid of 9 intermediate range ballistic missiles launched from mainland China on the coast. As the missile tracks begin to get closer, they're going to approach the detection range of the vessels. Once they've reached the detection range, each vessel will give its estimation on its best intercept for interceptor missiles. In this case, these are proxy models for Standard Missile 3s, SM-3s, and they're fired in waves at the incoming raid. Because the coordination is possible through the communication between each of the vessels, the independent commander algorithm can make a determination on who's the best target to shoot at any given missile. And you'll see as the blue interceptors go up to start collecting, that successful interceptions are represented by stationary icons with a red bar. And there's another wave of interceptors that are fired to continue collecting missiles in the raid. As the raid continues, a 3rd volley is fired, and finally, the last missile is collected right before it hits ground. So using this information of communication throughout the available fleet, the weapons platforms are able to prioritize complete coverage and collect all of the incoming raid with none of them hitting ground targets. This is the best case scenario. This is when everybody can coordinate and work together. They know who's supposed to be shooting at what, and they can prioritize maximum raid coverage. So let's see how that scenario changes with comms denial. So when dealing with peer and near-peer adversaries, the concern about denied or debilitated comms is significant. You can't always count on the fact that you'll have the ability to communicate. So we're going to still position our vessels in forward deployed positions around Guam, and they're going to receive the same raid as before, but one thing's going to be different in this scenario. When the incoming threats are detected, the fleet is suddenly unable to communicate with each other through blanket comms denial. In our simulator, called MDBE, or the Multi-Domain Battlefield Environment, we've actually severed all communications between the weapons platforms and they have to fall back on their own individual ability to identify and fire at the correct targets. As you can see, the successful interceptions are still going to be represented in the same way, but every vessel has to make its own calculations based on their own figure of merit and make an attempt to intercept the appropriate missiles. And you can see the interceptors are all clumped up as they are redundantly firing on singular incoming threat. So the result of this situation where the comms are denied and nobody can talk to each other is there's a lot of redundant fire. And in this case, 5 of the 9 missiles in the raid actually hit ground targets in Guam. This is really bad. This is the worst case scenario. So in our final scenario, let's see what happens when we use the predictive power of our artificial intelligence models for coordination without communication. We're going to instantiate our 3 vessels in stochastic positions in the same way as before. We're going to fire the exact same raid. And like with the second scenario, the commander and the other vessels are unable to communicate due to a blanket comms denial. However, you'll notice that the interceptors, when fired, are having a dispersed pattern again, as they're all targeting different threats in the raid. And what's happening here is a unique AI model called RCSNN, which is based on the NIST real-time control system, allows the predictive neural networks on each of the vessels to make a determination on what its friendly vessels are likely going to do and give a predictive recommendation on what threats they should try to focus on intercepting. And you can see that following that recommendation, each of these vessels is dispersing fire. And even though there's absolutely no communication between the vessels or their overall commander, they're able to collect most of the raid. You can see, unfortunately, 1 missile does make it through the collection, and 8 out of 9 threats are eliminated successfully, with only 1 of them hitting a ground target. This isn't optimal, but it's far better than 5 hitting ground when we didn't have coordination without communication enabled. This is a really powerful example of just how predictive AI can help with our missile defense. Here's a static example of what these arcs look like from the defensive fire as each of the vessels target and distribute their fire using coordination without communication and providing a substantial result over the previous use case. There are other cases where coordination without communication may support multi-domain operations with different types of platforms like UAVs, surface vehicles, and other unmanned platforms. We look forward to continuing to develop this technology in the future. Thank you.